This tutorial is for 6th grade, Module 4, Lesson 11. In this lesson, we're going to look at the equal sign and how it represents balance. The first part is just a review of the meaning of the equal sign. You can see I have a picture of a balance. On one side, I have 6 plus 4. On the other side, I have 2 plus 8. You can see that the two sides are balanced, and that's what the equal sign represents. It means the expression I have on one side of the equal sign is balanced with the expression I have on the other side, meaning they both add up to the same thing. 6 plus 4 is 10, 2 plus 8 is 10, and so that's a balanced equation. Both sides equal the same thing. And this is just a review of the equal sign. When things are not balanced, then we would use this sign, which means that they're not equal. In this section, we're going to fill in the blank between the two expressions with either the equal symbol or the not equal symbol. Here I have 4 plus 3 and 8 minus 1. Well, 4 plus 3 is 7, 8 minus 1 is 7, so those expressions are equal. Going across, 8 plus 4 is 12, 6 times 2 is 12, so those expressions are equal as well. In question C, I have 3 plus 3 plus 3. Well, that equals 9. Well, 3 times 3 is 9, times 3 is 27. So those expressions are not equal. In question D, I have 5 plus 5 plus 5. That's 15. 3 times 5 is also 15. So those expressions are equal. In the next section, we're to fill in the blanks to make balanced expressions. In question A, I have 4 plus something equals 2 times 5. Well, 2 times 5 is 10, so I need the other side to equal 10 as well. So 4 plus 6 equals 10. Now I have a balanced equation. In question B, we have 8 minus 4, well, that equals 4. 3 plus some number equals 4. Well, 3 plus 1 equals 4. So now they both equal 4. Question C, I have 2 plus 2 plus 2. That equals 6. So 3 times some number equals 6. Well, 3 times 2 equals 6. So that makes a balanced equation. And in question D, I have 9 plus 1. Well, that equals 10. 20 divided by something equals 10. Well, 20 divided by 2 also equals 10, so that makes a balanced equation. The next section is showing us that we can have an equation and change it, but as long as we change both sides in the same way, the equation remains balanced. My first balance is showing me that I have x, and it is balancing with 4. So in other words, the value of x equals 4 because they're balanced. If I go across, I've taken that same equation, my x and my 4, and on both sides, I've added 2. Because I did the same thing to both sides, it stays balanced. So that means that x, which is found here, plus 2, which is what we added to that side, is equal to 4 plus 2, or in other words, 6. And again, the two sides stayed balanced because 2 was added to both sides. As long as we're performing the same operation on both sides, the equation remains balanced. Let's look at another example. This time I'm starting with x plus 3 on one side and 9 on the other side. That tells me that x plus 3 balances with 9. If I go across, this time I've removed some numbers from each side. On the first side, I took away the 3 ones. To keep it balanced, I took away the 3 ones on the other side as well. That left me with 6 ones. So that means that x balances with 6, or x equals 6. In this section, I've started with a balanced equation, and I've changed one side of the equation. I'm going to describe the action that I did to change that side, and now to keep it balanced, I'll have to change the other side in the same way. We started with x equals 6. Now we have x plus 2 on the left-hand side of the equal sign. That means that I need to add 2 to both sides to keep it balanced. Since I added the 2 to the left side, I have to add it to the right side as well. Well, 6 plus 2 equals 8. So that's my transformed equation. It stays balanced because I did the same thing to both sides. In part B, I have x equals 12. Well, I changed the left-hand side to x divided by 3. So I need to divide both sides by 3. 12 divided by 3 equals 4. So x divided by 3 equals 4. In question C, I started with x equals 9. I changed the left-hand side to 6 times x. So I have to multiply both sides by 6 to keep it balanced. 9 times 6 equals 54. So again, as long as I'm performing the same operation or the same action on both sides, I'm keeping the equation balanced. Here I've been given an equation that's been transformed already, and I want to get it back to the original equation showing the value of x. And again, I'm going to change both sides of the equation in the same way. Another way to look at this is I need to get my variable or my x by itself. The question I need to ask myself is, if I started with just x, how did I change that equation? Well, here I subtracted 3 from the x, which means I subtracted 3 from the other side as well. So to get it back to its original form, I have to add 3. Because I changed it by subtracting 3, to get it back, I need to add 3. So I'll write that down. We're going to add 3 to both sides. So that gets me back to x on the left-hand side. Well, I still have to add 3 to the right-hand side. 11 plus 3 is 14. So x equals 14. I can double check myself by going back to that transformed equation and putting a 14 in place of the x. 14 minus 3 equals 11, and that's a true statement. So I know that x equals 14. If I look at question B, how did I change the x? Well, I added 5. To get it back to just x, I need to subtract 5 from both sides. So I'm going to write that down. So that gets me back to just x if I get rid of that 5. And now I have to subtract 5 from 12, and that equals 7. So x equals 7. And again, I could put that 7 in place of the x to check myself. 7 plus 5 equals 12. In question C, my x is on the right-hand side. It still works the same way. How did I change the x? Well, I subtracted 5 from it. To get it back to the original place, then, I need to add 5 to the x. So I'm going to add 5 to both sides. That gives me back to just x on the right-hand side, but I still have to add 5 on the left-hand side. 0 plus 5 equals 5. And again, I can check my answer. If I put a 5 in place of the x, 0 equals 5 minus 5, which is true. Question D says we have 8 equals x divided by 6. If I divided my x by 6, I need to multiply by 6 to get it back to the original x. So we'll say we'll multiply both sides by 6. That gets me back to the x on the right-hand side. I still need to multiply the 8 times 6, which equals 48. If I go back to the original problem and put 48 in the place of the x, well, 48 divided by 6 equals 8, so that's a true statement. So basically, the action that you're taking to get back to the original equation is the opposite of what you're seeing in that transformed equation. And in the final section, we're given some equations, and we're to decide whether the x equals 8 in each equation. So for example, I have x plus 5 equals 13. If I put 8 in place of the x, then I have 8 plus 5 equals 13. So yes, the 8 fits because 8 plus 5 equals 13. The next problem is 3 times x equals 11. Well, if I substitute an 8 for the x, that would be 3 times 8. 3 times 8 does not equal 11. So we'll say no, 3 times 8 does not equal 11. 3 times 8 equals 24. So in this case, we cannot put an 8 in the place of the x. In the last problem, I have x divided by 2 equals 2. So if I put an 8 in place of the x, that would be 8 divided by 2 equals 2. Well, that's not true either. 8 divided by 2 does not equal 2. 8 divided by 2 equals 4. So to figure out whether these statements work for 8, we just substitute the variable for the number 8 and see if it makes a true statement.